Okay, so good evening, everyone, and I welcome you all to today's live session for the course Elements of Mechanical Vibration, NOC25-AE17. So we are into the week 11 live session for this course, and we have already successfully completed 10 live sessions up till now. And so this week was mostly concerned about continuous systems. Right, up till now, we had the discussion about how do we deal with single degree of freedom system. Then we went on to 2 degree of freedom system, and then we extended that to multi-degree of freedom system, right? Now, this week, we are actually focusing on continuous system. See, earlier when we started this course, we understood that we have the liberty of deciding that for a system that we are working on, how many degrees of freedom should we give to a system? Like for example, if we have a cantilever beam and then we apply a force at the end of the cantilever beam, then what is going to happen? It is going to deform. Now we can actually model it as a single degree of freedom system, but if you look closely into it, a cantilever beam is actually a distributed mass system. It has infinite mass points, and so it is going to have infinite degrees of freedom with infinite number of natural frequencies. But it will depend upon what kind of application we are concerned about. Like for example, we are just concerned about how much it is going to deform when a particular amount of force is applied, right? In that case, what we can do is not thinking much about that. How should we model it? If it has infinite mass points, should we actually consider all the mass points and then take out all the frequencies and everything? Or what we can do is we can just model it as a single degree of freedom system and do the analysis that we want for the practical application. Right? We can do this until and unless that beam is deflecting by a very small amount. Right? So we can do that, and that is easier for us as well. See, as an engineer, it is our responsibility to make the analysis easy, right? In the easiest way, how we can get the accurate solution. Not accurate, but near to accurate solution, right? So that is what we did. About the single degree of freedom system, we discussed a lot. We discussed about undamped system, then we discussed about damped system, then we discussed about forced system, then we discussed about system which wherein the base was subjected to some kind of excitation. We discussed a lot about the singular degree of freedom system. Then that discussion was extended to 2 degree of freedom system, so that after understanding the single degree of freedom system, now we can understand the 2 degree of freedom system on the basis of the 1 degree of freedom system. Then it was extended to multiple degrees of freedom system. Now coming on to the continuous system. When we talk about continuous system, it is important that we understand the fact that when we are dealing with a continuous system, we will have to do the finite element analysis, right? So in finite element analysis, what do? We take the continuous system, divide it into finite number of parts. Reason being, using those finite number of parts, what we can do is we can sum up the effect and get the original picture of what the whole mass is going through, or the whole system is going through, correct? But what if we, like for example, if we consider a finite number of mass, okay? Finite could be 2 or 3 also. For a system which is having infinite mass points, if we consider only 2 or 3 lumped masses, is it going to give us a good solution? See, it would then depend upon the application, right? So what is important is that we model the system and then we check whether it is giving results that are comparable with the experiments, right? So like we discussed about in the last class about multi-degree of freedom system. So we got to know that for the multiple degrees of freedom system, we were evaluating the eigenvalues which were corresponding to the natural frequencies, and for every kind of a natural frequency, whatever we were having a particular shape of a particular eigenvector which was correspondingly for a mode shape, right? So for different kind of a mode shape, we were having corresponding to different frequencies, right? So exciting the system on that particular frequency is going to give us the particular mode shape, correct? This is what we know. Now, we know that the mode shapes and the mode frequencies are related to each other, correct? They are related to each other, and we use those because if we have the mode shapes and the modal frequencies, we can write the general solution on the basis of those. Or what we can do is we can write, if we excite the system with that particular frequency, we can write that how the solution is going to look, correct? Now, this is something which is opposite to what we were doing in the previous case. Now, for a continuous system, for example, if I divide our system into three parts of mass m1, m2, m3 and stiffness k1, k2 and k3. Okay. So we have to estimate the fundamental frequency. See, when we are talking about fundamental frequency, we are talking about a continuous system because continuous system can have multiple numbers of frequencies, resonant frequencies, and the fundamental frequency is the first natural frequency of the system. Okay. So for evaluating the fundamental frequency of vibration of the system, we have the particular mode shape. Okay. So for this mode shape that has already been given, see, the mode shape that has already been given is 1, 2, and 3. Okay, we have to evaluate the fundamental frequency. Earlier, what were we doing? We had the system. We found out the equation of motion. Using the equation of motion, we found out the eigenvalues or the modal frequencies. Based on the modal frequencies, we found out the mode shapes. Okay. In this question, we already have the mode shape, but we don't know the frequency. So now there is one Rayleigh's principle. Now, what does the Rayleigh principle say? Anyways, Rayleigh means it is something which is concerned about the energy of the system. So Rayleigh principle says that for a system of the form m x double dot plus c x dot plus k x is equal to 0, which is a conservative system. Conservative system. Okay, no, if it's a conservative system, this has to go to 0. Okay, this thing. Mx double dot plus kx is equals to 0, which is a conservative system. This is a conservative system. Now, for a conservative system, if we look into it, what is going to happen with a conservative system? See, the energy is going to be constant. So there's going to be a maximum kinetic energy and there's going to be a maximum potential energy. And those two are going to be equal to each other. That is what we do in the energy method, right? We equate the energies. In this also, we are going to do the same thing. So for this system, where m and k could be or x could be of any order, for this system, we have it as 3. For now, we'll do it for a general type of a system. For this kind of a system, we can write the kinetic energy as half x dot transpose m into x. This is the kinetic energy of the system corresponding to the x dot is the frequency, sorry, velocity, and m is the mass matrix. Similarly, we can write the potential energy of the system as half x transpose k matrix into x, which is the potential energy of the system. This is the kinetic energy, and this is the potential energy. I hope this is fine. Now, if we assume the solution of some sort, if we assume that this solution X is nothing but capital X cos of omega t. Small x is what? It is the general solution. Capital X is what? It is basically the mode shape. Mode shape if we are exciting at a particular frequency, or else it could be any x, which will be for this kind of a system, it is going to be a 3 cross 1 matrix. Definitely it will have 3 entries because small x is what? It is going to be x1, x2, x3. So capital X will be corresponding to that only. Okay, into cos of omega t. Now if this is the solution, okay, this is the solution, then corresponding to this we can actually evaluate the maximum kinetic energy and the maximum potential energy. So the maximum potential energy PE max is going to be what? Half X transpose K into X, correct? And the maximum kinetic energy is going to be what? Half X transpose M X omega square, correct? Now, if we equate the kinetic energy and the potential energy, what are we going to get? Kinetic energy max is equals to potential energy max. What is this going to give us? This is going to give us half X transpose M X transpose omega square is equal to half X transpose K X. Half and half will get cancelled, and omega square is going to be K X divided by transpose M X. Okay, and this is also called as R of X, which is the Rayleigh coefficient. Rayleigh coefficient, and this is equal to what? Omega square. See here, the omega square is definitely the fundamental frequency because we are equating the maximum energies, right? If it would have been a damped system, then this omega would not give us the fundamental frequency, but rather it would uh, not give, even we cannot even equate the energy also, kinetic energy and potential energy, when we are dealing with a non-conservative system. So this is what we are going to get. Now K matrix we can take out, mass matrix we can take out, and this capital X vector, which is related to the mode shape, that we can take out because it has already been given to us, and correspondingly if we'll put all of that in this, we are going to get the value of omega, right? So that is what we are going to do further. See, we have, firstly for the system, it has been given that we have to assume M1, M2, M3 are all equal to M, and K1, K2, K3 are all equal to K. So the mass matrix is going to be M1, M2, M3 on the diagonal ends, or maybe we can just write it as M1, 1, 1, 0, 0, 0, 0, 0, 0. 0. So this is going to be the mass matrix. Similarly, if we evaluate the stiffness matrix, the stiffness matrix for a 3 degree of freedom system is K1 plus K2 minus K2 minus K2, K2 plus K3 minus K3 minus K3 and K3 with a 0 and 0. Since K1, K2 and K3 are all equal, we can write this finally as K as common 2 minus 1 minus 1 2 1 minus 1 minus 1 0 0. This is the stiffness matrix. And lastly, X, which is already given as 1, 2 and 3. So first we'll evaluate the numerator, which is nothing but, if you look over here, this is the numerator. So if we evaluate this, we'll have X transpose into stiffness matrix into X, which is 1, 2, 3, 2 minus 1 minus 1, 2, 0, 0 minus 1, 1 minus 1 into 1, 2 and 3. This will be 1, 2, 3 into, this will give us 2 and minus 2, 0, 0. Then we'll have minus 1, 4, minus 3. Okay, there has to be a K also over here because of this. Okay, that also we can write K. Yeah. So if we'll put it over here, we'll have 2 into 2 is 4, 4 minus 1 is 3, and then minus 3, it is also going to be 0. And only the last element is going to be there, which will be because of 3 minus 2, 1. Okay, so this will give us the numerator as 3K. Now, if you look into the denominator, which is the mass matrix, which is 1, 2, 3 multiplied with the mass 1, 0, 0, 0, 1, 0, 0, 0, 1, which is an identity matrix. Identity matrix. This will give us M 1, 2, 3 into 1, 2, 3, which will be 9 plus 4 plus 1, 13, 14 M. So omega is going to be 0.2143 K by M, which will give omega as 0.4629 under root of K by M. This is the fundamental frequency of the given system for the mode shape 1, 2, 3. Okay, I hope this is clear. So earlier last week what we were doing was we had the system, we took out the equation of motion, then we used the matrix method to find out the determinant which was equal to 0. From that we got the characteristic equation, we solved the characteristic equation, and using the characteristic equation then what we did was we then evaluated the values of omegas, and then we knew that okay, for a 3 degree of freedom system we are going to have three eigenfrequencies or the modal frequencies, and on the basis of the matrix again using those frequency values we evaluated the three mode shapes, correct? Over here we were already having a mode shape that was given. We don't know about the frequency, okay? So we had to find out the fundamental frequency. So what we did was we applied the Rayleigh method, which was about equating the maximum energies, and then we used the mode shape that was given to put it in the Rayleigh equation, and then we got the fundamental frequencies. Anyways, Rayleigh method always gives us the fundamental frequency because it works on the concept of maximum energy, maximum kinetic and potential energy. See, if you remember, it was discussed when the discussion was about this different modes, right? Different frequencies. So in the lectures are discussed also about this, that at different modes, the total energy that the system is having is also different. And usually at the higher mode, the energy in the system is higher, right? So what we are doing is we are actually equating the maximum kinetic energy and maximum potential energy. So it is going to give us the fundamental frequency only. Okay, there could be many frequencies, right? For this 3 degree of freedom system, what we can have three frequencies, right? But here we are getting the fundamental frequency. Okay. Okay. Now coming on to question number 2, where we have to find out the fundamental frequency for a simply supported beam of uniform cross section shown below using the Rayleigh method again. So Rayleigh method is all about equating the maximum kinetic energy to the maximum potential energy that we know for now. Now, since we have to evaluate for a beam, earlier we were evaluating for a simple spring mass system. Here we have to evaluate for a beam. Now, for this kind of a beam, which is a continuous system, right? It is a continuous system. Earlier, what we were doing, we were solving it for a, over here we were solving, see, over here we had a lumped uh, everything, right? Our mass and springs, they were lumped. Okay, three masses and three springs were there, right? So it was lumped. But this case, which is for a beam, what is happening? There is no lumping of the system, but rather there is like continuous system for us. We have to solve actually the equation for the continuous system. If you look over here, we have a continuous system, right? The beam is in continuum. So now we have to evaluate the fundamental frequency for this. See, firstly, we need to find out the kinetic energy and the potential energy. If we get the kinetic energy and potential energy, we'll evaluate all over the length, and then we can simply find out the fundamental frequency. But first is to find the kinetic energy or the potential energy. So here the potential energy is going to be going to be there because of what? Can you tell me? The kinetic energy or the potential energy. Kinetic energy is still easy. Potential energy. It is going to be because of what? See, the beam is bending, correct? Now, because of bending, it is going to store some bending energy, right? Because of the bending moment that it is going through. It is going to store some energy because of that strain energy, basically. So we need to find that out, right? We have to find that out. Now, if you remember that for this kind of a system, what do we do? For a continuous system, we always take a very small part, get the energy for that small part, and then integrate over the whole length span, and then we get the total energy, right? So if we consider a very small part of this beam, what are we going to get? See, for example, from here we consider a part like this, a part like this, and this. So if this is d theta, we can assume this as dx, correct? And what is this going to be? R. For bending of beam, these are the usual nomenclatures. You must have gone through this in your strength of materials course. So this is it. So if you'll see over here, this is also d theta. Okay. So we know that tan theta is equals to perpendicular upon base, right? And then tan theta is nearly equal to theta for small theta, right? So what we can do is for this d theta, we can write perpendicular by base as dx by r. Why? Because this dx is very small and the d theta is also a very small element. It is just an exaggerated view of a very small element. That is why it is looking that it is curved. But if we cut a section of a curved line, a very small section, it will appear to be a straight line. So then using these, we can write d theta is equal to dx by d r, sorry, not dr, it is r. This gives 1 by r is equals to d theta by dx, d theta by dx, and this is also equal to d square y by dx square. Okay, so from this, so we have this equation. For now we'll leave it like this. Now for the beam, the flexural equation is given as 1 by r is equals to m by e I. M is the moment, bending moment, I is the moment of inertia, and capital E is the Young's modulus. And R is the R, even I should write R is the radius of curvature. Okay, so the flexure equation is given like this. Now we know what is 1 by R, correct? We know what is 1 by R, we know the equation. Anyways, for the potential energy, which is U max, we can write it as integration of du, which is U is what? Du is what? It is the potential energy for a very small element that we have considered over here, which we can write as integration of half m into dx by r, half m dx by r. Now 1 by r, what we can write it as d square y by dx square, right? D square y by dx square. But 1 by r is also what? M by ei. It is also what? M by ei, right? M by ei. So what we can do is we can just substitute over here first the value of m, half, integration of half. Here we have 1 by r. We can write 1 by r as m by ei, which will give us m square by ei into dx. M square by ei into dx. We can write it like that, right? Further, how can we write m square? We can write m square as e square I square by e square I square by r square. Correct? And we know already what is we know already what is see over here we are writing this. We know that 1 by r is m by ei, and this is also equal to d square y by dx square, right? So if you want to now replace m square, if you want to replace now m square, what we can do is m square we can write as e I square into d square y by dx square whole square, d square y by dx square whole square. Now we can replace this in that equation. So what are we going to get? Half into integration of 1 by e I into m square, which is e I square d2y by dx square whole square into dx. This will cancel out this and this will become half integration of ei d2y by dx square whole square into dx. So this is the final equation as of now. For now, we'll leave this equation over here only. This is the kinetic energy max. Okay. Now we'll evaluate the potential energy, which is definitely going to be half into mass into velocity square, whatever we are going to find out for that, which is going to be half y dot square into dm integration. We are doing y dot square into dm because we are actually taking a very small mass, very small part of the mass, which is dm, right? And then we have to integrate it. Okay. Now what we can do is we can write y dot as omega y dot as omega into y. So it will give us half omega square y square dm, right? So now if we equate the kinetic energy max with potential energy max, what are we going to get? We'll get omega square is going to be equal to integration of ei d2y by dx square whole square dx divided by integration of y square dm. Y square dm. This will give us the equation. Now for the beam given in question, comma, we assume y is equals to y naught sine of pi x by L sine of omega t. Now for the equation that we got over here, we need y and then we need to integrate it with respect to x, right? From that, we are going to get the equation for omega square, right? That is what we have to do. For that, we need to have a y. Now, unlike the case that we did with the lumped case of mass and spring, there we were having lateral vibrations. Not lateral, actually translation vibrations in the direction of the mass itself. So we chose the solution as x sine omega t. But over here, the beam is going to, since it's a simply supported beam, and then there is this mass at the center, you can look over here. The y is going to vary something like this, which is somewhat like a, we can give it like a sine curve. We can give it like a sine curve, correct? Sine curve, which is going from 0 to maximum value and then going to 1. Only one phase. One phase, as in what I'm trying to say is that for a sine curve, the behavior is something like this. So we consider only this part. Okay, that is what is happening. So we take the y in this form. Now, since we know the equation of y in terms of x, we can simply put it in the equation that we got earlier, which is this one. If you put it over here, we can get the equation for omega square. So firstly, from here, we need to evaluate d square y by dx square, which is going to be what? Minus pi by L square y naught sine of pi x by L sine of omega t, right? Substituting in 1, let us say, let us assume that this is 1. What are we going to get? Omega square is equal to E I pi by 4, no, pi by L to the power 4, pi by L to the power 4 into integration from 0 to L sine square pi x by L dx divided by m. Let us say this m is nothing but the force per unit length into integration from 0 to L sine square pi x by L into dx into dx, right? So if we look that the integration term is common in the uh, above and below, so we can just cancel these out, right? Then finally we are going to get the equation for omega square as pi to the power 4 e I by m L to the power 4, which implies omega 1 is equal to pi square under root of e I by m L to the power 4. And this is nothing but the fundamental frequency of the system that we were supposed to obtain as per the question. I hope this is clear. We did nothing much, but all we did was equate the kinetic energy and the potential energy. Coming on to question number 3. Okay, a system showed a resonant frequency of 30 Hz when vibrated by an eccentric mass shaker with a weight of 10 Newton. The resonant frequency lowers to 24 Hz when an additional mass of 10 Newton is attached. Determine the true natural frequency of the system. Okay, this is something which is related to the Dunkerley's equation. Now, what does this equation say? This equation says that if I have a system, if I have a system which has a frequency omega 11, which is the fundamental frequency of the system or structure. Omega 11 is the fundamental frequency of the system or the structure. Then we have omega 22, which is the fundamental frequency of the exciter mounted on the structure. Now there is an exciter that is mounted on the structure where we are not considering any other masses. We are just considering the mass of the structure. Sorry, exciter without any other masses. Then in that case, omega 1, which is the fundamental frequency of the structure with the exciter mounted. We can write as 1 by omega 1 square equal to 1 by omega 1 square plus 1 by omega 2 square. So this is basically a relation in which we relate the fundamental frequency when the exciter is put. So basically what happens is that for a system, we want to know that what is the natural frequency, correct? But I don't know what is the natural frequency of my system. It is a very complicated system and I don't know what is the natural frequency of my system. So how do I evaluate it? So what do we do is we actually see the basic understanding of a system where we don't know what is the natural frequency. We apply an external force on it and then we change the frequency of that external force. And at whatever frequency we are going to have a peak of the amplitude, that is going to be the fundamental frequency of the resonant frequency. So for that, we will need to excite the system. Correct. If we do not have any internal way of providing any kind of a forcing to the system, like for example, if we have a, let us say, airplane wing, or we have a windmill or something like that, where we don't know the resonant frequency. So, and there is nothing which is we are giving to the system as a mechanical input, right? So what do? We take that system and then we apply a exciter. We put a exciter. We like mount an exciter on that structure, and then we excite the exciter with different frequencies, right? So it is going to give us a fundamental frequency at which we are going to have maximum amplitude. But that fundamental frequency is going to be of the structure plus the exciter combined, correct? But we are concerned about finding out the fundamental frequency for the structure only without the exciter. So then what do? There is no point of then doing this because we are exciting the system by an exciter, but then we are actually getting a frequency which is different from the frequency that we want. So there's no point. So then this equation actually helps us in that because this tells us that, okay, we have a structure and then we are mounting an exciter. So if we know that what is after mounting the exciter and after exciting, we know that what is the uh, fundamental frequency for that whole system. But then if we just take the exciter and put it over here, and for the structure, we don't consider the masses, and then we find out the fundamental frequency that for that exciter, then we can use this equation, this particular equation, in order to find out the fundamental frequency of my structure alone. I hope this is clear. For the structure alone, then we can find out using this equation. So this equation is very helpful, especially for industrial purposes, because then we are able to find out the frequency of the structure, which is not possible for us to every time find out by some equation by doing under root k by m or by exciting the system practically and then checking the time period of oscillation or something like that. Because, yes, because see, we learned about this earlier also, that for a system, if we have damping present, it could be of many types. Like for viscous damping, we have that relation of logarithmic decrement. For frictional damping, we have another relation, and likewise. But for a practical situation, we have every kind of a damping. We have damping which is happening because of air resistance. Then there is damping which is happening because of structural uh, damping, and then different kind of a factors actually contribute towards the decrement of the energy of the system. And so using any kind of that kind of a behavior is actually not going to give us the correct estimation of the fundamental frequency. So it is better that we excite the system. If a system is something which wherein we can actually give it some kind of forcing, excitation forcing, mechanical forcing by default of its design, then that is good, but it is not possible always. So in that case, for a structure, we apply an exciter, and then we can use this equation. So we have to find out two things. First one is when we apply the exciter on the structure, we vary the frequency, and then we know where is the peak, and then that peak we know the fundamental frequency of the structure plus exciter system. And then we evaluate the fundamental frequency for the exciter, and then we can use this equation to find out the fundamental frequency of the structure alone. I hope this is clear. So this is the basic theory. Now for the question, we basically have a system showed a resonant frequency of 30 Hertz when vibrated by an eccentric mass shaker with a weight of 10 Newton. Okay, also for this kind of a equation, what we can do is we can further write it as 1 by omega 1 square is equal to 1 by omega 1 1 square plus A22 into M2. Because k can be written as, sorry, omega can be written as under root of k by m, and 1 by k can be written as A22, which is the stiffness coefficient, if you remember. So using that, we can write it in terms of A22, something like this. So we have that resonant frequency of 30 Hertz when vibrated by an eccentric mass shaker with a weight of 10 Newton. So first we have structure plus shaker or exciter of 10 Newton. We have a frequency of 30 Hertz, which is omega 1 square, 30 Hertz. Okay. Then we have another case where we have structure plus exciter of, then we have the resonant frequency lowers to 24 Hertz when an additional mass of 10 Newton is attached. Additional mass of 10 Newton. Okay, earlier it was 10 Newton and then we attached another 10. So now it becomes 20. 20 Newton. Now it becomes 24 Hertz. Okay, I hope this is clear. Now we have to use the equation that we have over there. So with that equation, what we can do is we can write the first one as 1 by omega 1. Now we have the frequencies in hertz, so we'll have to change it in radians per second, which is going to be 2 pi into 30 and 2 pi into 24. So we'll have 1 by 2 pi 30 or 60 pi square is equal to 1 by 2 pi f11 square plus A22 into 10 divided by 9.81. This is the first equation. Second equation is going to be 24 into 2, which is going to be 48 pi whole square is equal to 1 by 2 pi f11 whole square plus a22 into 20 by 9.81. This is the second equation. Now what we can do is we can subtract the second equation, or no, the first equation from the second equation. We can subtract the second equation, first equation from the second equation. Then what is it going to give us? We have this as 2 and this as 1. So we can write 2 minus 1. This is going to give us 1 by 48 pi square minus 1 by 60 pi square is going to be equal to 10 by 9.81 A22. Correct? This will give us 1 by 22739.3 minus 1 by 35524.3 is equals to 4.398 into 10 to the power minus 5 minus 2.815 into 10 to the power minus 5. This will give us 1.583 into 10 to the power minus 5. So A22 is going to be nothing but 1.583 into 10 to the power minus 5 divided by 10 by 9.81. 1.553 into 10 to the power minus 5. So this is the value of A22. A22. Now, from A22 we can evaluate the value of stiffness also, right? So stiffness is going to be what? K is going to be 1 by A22, which is 6.44 into 10 to the power 4 Newton per meter. Okay, I hope this is clear. Now the main thing was to find out F11, which we can now, as we know the value of A22, we can substitute on any of the two equations, and then we get 1 by 60 pi square is equal to 1 by 2 pi f11 square plus 10 by 9.81 into 1.553 into 10 to the power minus 5. This is going to give 2.815 to 10 to the power minus 5 is equals to 1 by 2 pi f11 square plus 1.533 into 10 to the power minus 5. So this gives 1 by 2 pi f11 square. It's going to be, will be 2, 8, 1.232 10 to the power minus 5, and so F11 is 284.9 by 6.283, which is 45.4 Hertz. So this is the frequency of our system, of the structure, right? This is what the frequency of the system alone. Okay, I hope this is clear, and I also hope that why these kind of analysis is essential for us is also understandable. Coming on to question number 4. Find the fundamental frequency of a uniformly loaded beam with a concentrated mass equivalent to the beam mass placed at the free end of the beam. Okay. So earlier, the question that we did over here, right, it was for a system wherein we applied an exciter. Now, this is for a case when we have a system and which is a beam, and then we applied a mass on the beam at the end. And so how we have to find out the uniform for the uniformly loaded beam with that particular mass only. Now, for this, just a second. Okay. So this is the question. Beam mass. This is also mass m. This is also mass m. We have to find the fundamental frequency for this, right? Now, if you remember that from the concepts of strength of materials, you can evaluate the frequencies for the two cases. You can basically divide it in two parts. One is going to be this plus this is what? Massless for this case. Okay, we can consider it into these two parts, right? So the concept that we discussed for the previous question, wherein we had 1 by omega 1 square was equal to 1 by omega 1 1 square plus 1 by omega 2 2 square. So omega 1 is going to be what? Frequency of A. Let us say this is A, this is A1, this is A2. So this is frequency of A. Omega 1 1 is frequency of A1. Omega 2 2 is frequency of A2. So in the previous case, we were having a case wherein we had a system where we don't know the fundamental frequency. So we applied a exciter to the system. We excited the system. We checked where the peak was coming, found out the fundamental frequency of the both the exciter plus the structure. After that, we evaluated the frequency of the exciter only on the structure without considering the masses of any of the structure. And then using the equation, we found out the frequency of the structure only. In this case, what we are doing is we are supposed to find out the fundamental frequency of a beam with mass m, and with at the end there is also a mass of the same amount of the beam. So now what we can do is we can use the concept of strength of materials, right? And what we can do is we can just take out the values of frequencies for firstly when we have a beam of mass capital M, we find out the fundamental frequency for that. Then we find out the fundamental frequency for which we have a beam and then a mass of capital M, which is at the free end of that beam. But the mass of the beam is very small as compared to capital M, so we consider it as massless. And then if we find out the frequencies of A1 and A2, we can simply put it in the equation that we evaluated and then get the final fundamental frequency, right? So firstly for A1, so for the A1, which is the beam, we have omega 1 1 as 3.515 square E I by M L cube. This is for the beam. This you can get from any strength of materials, or you can also find out from using the concepts of strength of material. So basically this frequency we are going to get from the concept that we find out the relation of equation of motion for a single degree of freedom system. You can consider it as a single degree of freedom system. And then if you find out You can get this from the relation of equation of motion. Okay. And then omega 22 is going to be what? 3 times of EI by ml cube. This is for when there is a concentrated mass at the end of the massless beam. Okay, I hope that is clear. So now we have to just put it in the equation, which says that omega 1 square is equal to omega 1 square, omega 2 square by omega 1 square plus omega 2 square, right? So this is going to give us, from here we can put the values. This is going to give us 3.515 square into 3 divided by 3.515 square plus 3 square. Correct? If you look in the above equation, we have a square, like if we consider the EI by ml cube, which is common, we have it to the power 4 in the above and to the power square in the below denominator. So we are going to just consider only the twice power, EI by ml cube square. Not square actually. Yeah, above it will be square, below it will be power 1, so we'll get only 2. Sorry, only 1 power. So if we solve this mathematical part, we are going to get omega 1 square, or yeah, omega 1 square is 2.4 EI by ml cube, or omega 1 as under root of 2.4 EI by ml cube. This is the fundamental frequency of the beam. Fundamental frequency of the beam with both masses. Okay, I hope this is clear. So now you have seen both the examples of the theorem that was given. So for that theorem, we have two kind of a cases that can be used in practical problem in order to solve. Like for example, if I have a system which I am making by considering system A and system B, and now I'm adding both the system and getting the system C. So instead of working on into finding the fundamental frequency of system C, what I can do is, if I already know the fundamental frequency of A and fundamental frequency of B, I can use this same concept to find out the fundamental frequency of the system, which is actually the combination of or assembly of the system A and system B, and which is also known as the system C. Now coming on to question number 5, wherein we have the fundamental frequency. Okay, the fundamental frequency of a uniform bar of mass m simply supported as shown below is this. If a lumped mass m naught is attached to the beam at x is equals to L by 3, determine the new fundamental frequency. See, this is what I was saying. What did we do? We had a simply supported beam in the previous question, right? Sorry, cantilever beam. Here we have a simply supported beam. After simply supported beam, we are now putting a mass m naught at a distance L by 3, right? So now we are using this concept that was given by Dunkerley, that so that we can find out the fundamental frequency of the final system, right? And we are not concerned about finding it by, again solving it, or finding the equation of motion, or finding out the stress strain relation and everything. We know it for a simply supported beam. We know it for a simply supported beam that is massless, and then we consider a mass m naught, and then we can just use the equation to find out for the assembly, right? So just a second. We have the first case where this is the beam Okay, right? And this is of mass capital M. And for this, the fundamental frequency, which is, let us say, omega 11, is what? Pi square under root of E I by M L square. Not square, it is cube. M L cube. Okay, this is already given in the question. Now, the second case is what we have is this is simply supported beam. We have a mass m naught which is placed at a distance L by 3. L by 3 from this end. So here we have m naught which is at the distance L by 3 from here. Right? Something like this. And combining these both, we get the final system, which is this. Okay. So omega 11 is already given to us. We need to find out omega 22 and then omega 1. So for omega 22, what do we have? We have a simply supported beam which is massless, or we can say which has a mass, but which is very small as compared to the mass that is put on the simply supported beam, because the mass that is put on the beam, it is of mass m naught, which is much higher as compared to the mass of the beam itself. So we can say that it is massless. So for this kind of a system, what is going to be the omega 22? So for now, we assume that okay, we have A22M2 M naught. Okay, so we can write the equation first. How am I going to write the equation? It is going to be 1 by omega 1 square is equal to 1 by omega 1 square plus A22 M naught. A22 into M naught. Correct? Now, if we have A22 into M naught, then what we can do is we can for now simply take omega 1 square on the both sides, multiply. So we get 1 is equal to omega 1 by omega 1 square plus A22 M naught into, yeah, A22 M naught into omega 1 square. Right? We can write it like this. Now what we can do is it is going to be omega 1 only, no? Wait. Yeah. Okay. So what we can do is we can take omega 1 by omega 1 square common. We can write as 1 is equals to omega 1 by omega 1 square common 1 plus A22 M naught omega 1 square. Like this, we can write it. Okay. So this will give us omega 1 by omega 1 square as 1 by 1 plus A22 M naught omega 1 square. Like this. Now we already know the expression for omega 1 square. Correct? So we can substitute it in over here. Okay. And we need to find A22 as well. So, for a simply supported beam or a mass that is put on the beam at a distance L/3 from one end, you can just find out the stiffness K as nothing but 68 into 81 by 8 EI by L cube. So if we know the stiffness, we can simply evaluate A22 as 1 by K and write it as 8 L cube by 6 into 81 EI. Correct? This thing we can write. And we can simply put it in that equation. This will give us omega 1 by omega 1 square as 1 by 1 plus 8 8 pi m divided by 6 into 81 8 pi m by 6 into 81 by m, right? Anyways, this is m naught. Okay, so you can write it like this. So this will give 1 by 1.6, 1 plus 1.6 m naught by m, right? This is going to give us the ratio. And now when we know the ratio, we already know the expression for omega 1 and we can write omega 1 in terms of this equation that I wrote over here. Here what we did was we put the value of A22 and into omega 1 square. So basically we get A22 into m naught into omega 1 square. So this is basically 8L cube by 6 into 81 EI into m naught and into, we have this expression already, which is this pi square EI by ml cube. So pi square will be pi to the power 4. Here also it should be 4 EI by m L cube, right? So this L cube will get cancelled, EI will get cancelled, and so finally we'll get 8 pi to the power 4 m naught by 6 into 81 capital M. And we can further write it that like this. And omega 1 is going to be nothing but 1 by 1 plus 1.6 m naught by capital M into omega 1, or finally we can write it like omega 1 as 1 by 1 plus 1.6 m naught by capital M into E I by m L cube under root of this to pi square. This is the frequency of the system that is given to us, which is the simply supported beam of mass capital M, which has a small mass m naught placed over it at a distance of L by 3. Okay, I hope this is clear. Okay, now coming on to question number 6. Okay, so this is related to an airplane wing. See, what we discussed for the first question, that's for example, if you have a structural system which is like an airplane wing, and I want to know that, okay, what is the, you know, natural frequency of that wing, right? what is the natural frequency of that wing, or the fundamental frequency, or what is going to be the stiffness of the wing. How am I going to know? Because I can measure for the wing, I can measure its weight, but I don't know what is going to be its, I don't know what is going to be its stiffness or something like that, right? So this is what we are concerned about. So here in this question, we have the natural frequency of a given airplane wing in torsion is 1600 CPM. CPM means cycles per minute. So we have the frequency. Fine. What will be the new torsional frequency if a 100 lb fuel tank is hung at a position 1/6 of the semi-span from the center line of the plane, such that its moment of inertia about the torsional axis is 1800 lb inch second square. The torsional stiffness of the wing at this point is this. See, in this question, we already know the natural frequency of the airplane wing. But now a fuel tank is attached. So now what, how do we know the natural frequency? Because for an airplane, it is very important that we know the resonant frequencies so that any kind of a catastrophic failure can be avoided, right? So what are we going to do? So this is, the question is somewhat like this. So if we, let us say, have a plane like this, and then we have the wing. This is the center line. Okay. Now, so we'll consider only one part. This is the center line. Okay. Now for this airplane wing, we have the fuel tank is hung at a position 1/6 of the semi-span from the center line. Okay. And we have to find out that what is going to be the new natural frequency. So firstly, what do we know is the earlier natural frequency, which is 1600 CPM. So we know omega 11, 1600 CPM, correct? And yeah, so I can find out the value of F1. No, this is omega 11, no? Yeah, it's fine. Anyways, we can write it, leave it like this also. We can just write it in terms of F only and keep it like that, because the conversion of everything is frequency in CPMs. We can just, we don't need to change it into omega. Okay. Second is, we know that a 100 lb fuel tank, 100 lb fuel tank, and then we have torsional stiffness of the wing at this point, 60 into 10 to the power 6 lb inches per radian, which is the K stiffness. Correct. Now, from the mass and stiffness, can we evaluate the frequency for the fuel tank? Right? We know the mass of the fuel tank. It is already given. We need to find out the torsional stiffness of the fuel tank, so torsional stiffness at this point, that is already given. So what do we need to find out? We need to find out the frequency omega 22, right? Which was the, as discussed earlier, it was the frequency of the exciter, not considering the mass of the structure. The exciter mounted on the structure, but not considering the mass of the structure, but considering only the mass of the exciter. So here we will consider the mass of the fuel tank, which is already fixed on the wing, and then we don't consider the mass of the wing, but only the stiffness at that point. Okay. So for that, we can find out F22 as what? Under root of 60 into 10 to the power 6 by 1800. This will give us in radians per second. So we'll change it by 1 by 2 pi, and this will give, this will be giving 29.1 CPS, or okay, 1745 cycles per minute. Now we have F22, right? So we have F11, we have F22. We just need to do the calculation now because we had the equation 1 by omega 1 square was equal to 1 by omega 1 square plus 1 by omega 2 square. Now, since omega 1, omega 1, omega 2 were all in radians per second, we can change it to frequency domain by using 1 by 2 pi f1 square, 1 by 2 pi f11 square. The 2 pi's will get cancelled. Finally, we are going to get 1 by f1 square is equals to 1 by f11 square plus 1 by f22 square. So putting the value 1 by 1600 plus 1 by 1745 square, this will give us F1 as 1180 cycles per minute. This is the new fundamental frequency, and if you see that the fundamental frequency has actually been reduced because of the fuel tank. After putting on the fuel tank, the frequency has all been reduced. So it is very important to note over here that earlier if the working range was 0 to 1600, now after the putting on the fuel tank, this range has been reduced by a significant amount. Okay, it has been reduced by a very significant amount, and that is why it is very important that after putting on the fuel tank we do the analysis about how the frequency is changing, because if this analysis would not have been done and if due to any reason the frequency goes beyond 180, then there could be a chance of what could be a chance there will be a catastrophic failure for sure, because the amplitude of vibrations is going to be very large, right? So this particular Dunkerley's equation is very much important in order to understand how the fundamental frequency of a continuous system is changing if some addition of some thing is done on it. Okay. Okay, now coming on to question number 7. So we have a structural system which is shown over here. We have three masses m1, m2 and m3, and then there is another mass m0 which is at the base, but this m0 is actually movable because you can see that it is attached to the reference with a spring with a stiffness k0. So that is why it can move, and because of that there is a movement of m2 and m3 as well, right? And we're going to find out the fundamental frequency of the three-story building, right? So we know the equation, right? The equation that we were currently doing for two systems where there was one structure and one exciter. Here, what do we have? We have M0, M1, M2, and M3. Four things that we are concerned about. So for M0, we can simply take out the frequency and then we need to add on the effects of M2, M1, M2, and M3 to find out the fundamental frequency of the whole structure, correct? So same equation we are going to follow, right? Which is going to be 1 by omega 1 square is going to be 1 by omega 1 square, 1 by omega 2 square, 1 by omega 3 square, 1 by omega 4 square. But earlier we have seen that this omega 1 by omega 1 square can be replaced by a into mass, right? So we can write as 1 by omega 1 square as a11 m naught, or we can just write it as, we can just maybe change it because m is given in terms of naught, so we can write omega naught naught omega 11 22 33. So here also we can write a as a naught plus m naught, a11 m1, a22 m2, a33 m3. So m0, m1, m2, and m3 are already given in the question. We need to find out the values of a0, a11, a22, and a33. If we are able to find it, then we can simply get the final equation. Now, for m naught, it is very easy because we already know the stiffness. Correct. If we forget whatever is above m naught for now, we just hide this thing, right? Whatever is above m naught, which for now we are not concerned about it. So we basically have a reference which has a spring connected to it of a stiffness k naught, and that spring is further connected to m naught, a mass which is m naught. For that, if I want to find out a naught, the coefficient, it is going to be what? Simply 1 by k naught, 1 by stiffness. 1 by k naught. So a naught is going to be nothing but 1 by k naught. Okay, it is easy. Coming on to A11. Now, what is A11 and how do we find out A11? So see, we have a three-story building, right? Now, if you look into it, what we have done is we have basically considered that there are four masses, and these masses are connected to each other by what? Beams. They are connected to each other by what? Beams, because of which these masses are bending. So if it is about beams, then that those beams are going to carry what? They are going to carry the stiffness. And on the basis of those stiffness, we can evaluate the effective stiffness. And if we have the equation for effective stiffness, we can finally find out A11. So let us assume that there is going to be a contribution for K1, and then there is going to be a contribution which will be because of the bending, right? So for bending, we are going to have the effect something like 24 EI by H cube, 24 EI, which is going to be because of the Young's modulus and the moment of inertia, and H cube because we are considering that every beam is of length h, which is the distance between the two masses, right? So those two masses have a distance of h in between them, right? So for that, A11 is going to be what? 1 by K1. There's going to be a stiffness contribution, and then there is going to be plus h cube by 24 E I, h cube by 24 E I. Stiffness is going to be 24 EI by h cube, so we are going to take inverse of that. Okay, and similarly, A22 can be written as what? A22 can be written as what? Here also we are going to have the effect. We are going to have the effect which will be because of stiffness, and then we are going to have effects which will be because of, okay, I should write it as I1. Okay, and then we are going to have the effect of stiffness which will be because of the beams. Now if you look over here, for m1 there was only one beam which was being attached to m naught, but for m2 we have a beam which is attaching it to m1, and then we also have a beam which is connecting it to m naught. So the whole movement of m2 will depend upon the beam which is connecting m2 and m1, and the beam which is connecting m1 and m naught as well, right? So in that case, we can write A22 as 1 by 1 by, just a second, this should be K naught, 1 by K naught, because stiffness for other elements are not present over here, plus H cube by 24 E I1 plus H cube by 24 E I2. Okay. Similarly, A33 is going to be what? 1 by K naught plus H cube by 24 E I1 H cube by 24 E I2 H cube by 24 E I3. These are going to be the contributions of A naught, A11, A22, and A33. Now, what do we have to do? We have to just sum it up, right? After multiplying with the corresponding mass. So, this will give us 1 by omega 1 square m naught by k naught, 1 by k naught plus h cube by 24 e I1 m1 plus 1 by k naught plus h cube by 24 e I1 plus h cube by 24 e I2 into m2 plus 1 by k naught h cube by 24 e I1 h cube by 24 e I2 h cube by 24 e I3 into m3. This is going to be the total contribution, and then from this we can evaluate omega 1 square. Now for now, if we assume that okay, I1, I2 and I3 all are equal, and then M1, M2, M3, okay, the masses we cannot equate. We just assume I1, I2 and I3 are equal, and yeah, so we get 1 by omega 1 square as 1 by k naught m naught plus m1 plus m2 plus m3 plus m h cube by 24 ei plus m2 into twice of h cube by 24 ei plus m3 3 times of h cube by 24 ei. So this is the final contribution, and this is going to be the equation from which we can evaluate the value of omega 1 square. Okay, I hope this is clear. Coming on to the last question. So this is a bit lengthy question. Let me check the time. Okay. Okay. So we have to find the, okay, the question is wrong over here. So this is about the transfer matrix, related to the transfer matrix solution. So basically herein we have to find out the transfer matrix and how are we going to proceed with the transfer matrix solution. So if you remember that there was this concept of transfer matrix, right, which was used to basically transfer one part of the system to the another part of the system. How can we actually relate two parts of the system? Okay, so for this question, outline the transfer matrix solution process for the given system. So basically I'll try to do some part up to some part where it is complex, and like that it will also revise the concept of transfer matrix for you people. So there were two things that were concerned about the transfer functions, right? One was where we were concerned about transferring of the force, and the second one when we were concerned about transferring of the position or the angle, right? So for this system, what we can do is we can divide it into multiple parts, right? How are we going to divide it? So let us suppose that this is our system. This is J. This is J naught. Okay. Then we have this thing, which is a gear. And as you can see over here, there are two. One is this one. Other one is this one. Maybe I should use another color. Okay. Then we have from here this, which is J4. They have over here J2. Okay. So for now, what we can do is we can assume that this point is point 0. Okay. And this is the right hand side. This point is point 1. This point is also point 1. However, this is the left of point 1. This is the right of point 1. Okay. This we can take as point 2. And this is what? R. Because we are concerned about R only. For the left, we already are going to get, so the left part of 2, we are already going to get it from the R part of 1. Okay, so we are not concerned about it. Further, for J4, we can have 4 with R. Okay, again R, because left one we'll get from R part of 1. R is right and L is left. Okay, for this, we have R, and this we can take as 3. Now we can write for J naught, we already have J naught. We can write this as K1. For this, we can write as N square K4. N square, I hope that you understand it is because of the gear pairing and everything. Okay. For J2, we have K2. Okay. J4, we can write as N square J4. Okay. And this is going to be J3. Okay. I hope I'm not missing anything as of now. Yes, this is it that we require. Now, first is to understand how do we give the positive and negative values. So we have something like this. Okay, so what do we have over here? We have T B of 1 R, and then we have theta B 1 of R. Okay, so A and B is what? A and B. A is for the lower gear and the B is for the upper one. Okay, so for this, what do we have? We have TB1 of R, TB1, okay, 1, because it is the one position that we are taking, not position, actually the element that we have given the name 1. For that also, we are considering the B part, which is the upper gear. And for that, we are considering the R part, right hand side. Okay, so this is basically the green one. This is basically the green one. Okay, considering the blue one, I'll make it from blue only. Here we are going to have two shafts, one over here, another over here. Okay, so for this part, we are concerned about the right hand side. Okay, so here we are going to have torque T A1 of R, and then we are going to have theta A1 of R. Okay, here we are again going to have torque, which is going to be T A1 of L because it's of the left hand side, and then we are going to have TB1 of R. TB1 of R is going to come over here. Why? Because it's a free body diagram, right? If the upper gear is having some force like this whole one part that we are considering, it should have a force balance. No, it should have a force balance. So for every action, there is a reaction in the opposite direction. So that is what we are considering over here. So if we consider the force balance because of the torque for this system, what are we going to get? We consider the force torque balance on A. What do we get? T A R of 1 is equal to T A 1 of L plus T B 1 of R. Correct, because see, it is very easy. Here we have T A1 of R, which will be equal to sum of these two. This is going to be what? Sum of these two. Ta1 of L and Tb1 of R. This one. This is the one equation, right? Now, if you remember when this whole discussion about transfer function was going on, so finally there was an equation that was derived, which you can go and look into the book also. The equation that says that theta t for R right hand side for the n minus 1th part is equal to what? Is equal to a matrix into theta and t of what? The R right hand side of the nth part. Basically, we are relating the right hand side of the nth n minus 1th part to the right hand side of the nth part. Okay. So this was what? 1 minus omega squared j by k. 1 minus 1 by k omega square j and 1. Okay, this is the relation. That is a general relation. By using this for our case, what are we going to relate? So if you look over here, we know the torque balance, okay, for A part. If you look at the B part, this green thing, this B part, is what? It is connected to what? The fourth part, right? The fourth wheel it is connected to. So what we can do is we can relate the rth part of B to the sorry, not rth part, R right hand side of B to the right hand side of 4. How? By using that equation. You can use those equation to write the equation for the R right hand side of 1 to the R right hand side of 2 also, right? But since B is connected to 4, so we'll write the transfer matrix for that. So what is it going to be? If you look, we can write it as theta and T B. Right hand side for 1 is equal to a matrix which will relate theta and 0. 0 why? Because over here there is no torque. Sorry, not this one. Over here. Alright, so it is going to be what? 0. Like on the right hand side. On the left hand side it is going to have, but on the right hand side it is not having. So this, what is going to be inside the R of the 4. Okay, so what is going to be inside the matrix? It is going to be 1 minus omega square. Since j is what? N square j, n square j by k, which is what? N square k4. This is also j4 minus 1 by n square k4. Here it is going to be omega square n square j4 n square j4, and here we are going to have what? 1 only. This is how we are going to relate it. Fine. Further, if you look closely, you're going to get that theta right hand side of B1 is what? Minus theta L A of 1, which is also equal to minus theta A K of 1. Okay, so firstly theta B right hand side. So which is over here? Theta B right hand side over here. If you look closely, it is equal to what? Minus of theta L A of 1 for theta of L A1. This over here it will be equal to with the minus sign. And it is also equal to what? Theta of, this should be R, A of 1 minus of theta A of 1, right? So from this matrix, what we can do is we can write the equation. How? We can write theta B right hand side for 1 is equal to what? 1 minus omega square n square j4 divided by n square k4. Okay, n square and n square are going to get cancelled. So we can just write j4 by k4 this whole into theta b4 of r, which is what? Which is what? Minus of theta L a1. Correct. Similarly, for the torque, T B R of 1 is what? Minus of omega square n square j4 divided by what? 1 minus omega square j4 by k4 into theta a1L. Right? This is what it is going to give us. So how is this? Basically, TBR1 is what it is going to be. Wait, it is going to be from this. Okay, maybe I should write it only. So this is what it comes after. Before this, there is this equation which says that TRB1 is what from over here omega square n square j4 into what? Theta B R4. Theta B R4 I can get from here. This is what we'll replace and then we get the equation of this type. Right? This is what we are going to get. So then what do we get finally? What do we get finally? We get that theta of A and T of A, right hand side and 1. Because this is what? Right hand side and 1 for B, right? But this is what we have now in the form of equation. And we want to write this. This is what? This minus this. TRA1, TRA1 is equal to TAL1 plus this. So what we can do is we can write this right hand side of TA1 in terms of TAL of 1. Right, we can write it now. And we have this equation. We have the equation of TB1 of R. Right, so we can write now in terms of that. How? See. Since here we have theta LA of 1. Okay, we have to just add TAL of 1 in this and then we get the final one. So basically what I'm trying to say is I should write it first. TRA of 1 is what? TLA of 1 plus TB1 of R over here, which is already we know over here what it is, which is minus omega square n square J4 divided by 1 minus omega square J4 by K4 into what? Theta L A of 1. So now we can write it in matrix form. We can simply write it in matrix form. Also, we know that theta A R1 is equal to theta A L. Okay, I've written this in the opposite direction. I'm sorry. It's a bit confusing sometimes. T R A T L A. So theta R A of 1 is what? Theta L A of 1. It is going to be what? It is going to be the same, isn't it? Because the gear, the right hand side and the left hand side are going to rotate by the same amount only. Okay, we are not considering any kind of internal deformation in the gear. So this can be written as nothing but a matrix into theta A TA of 1, but on the left hand side as 1 0 1 and minus omega square n square J4 by 1 minus omega square J4 by K4. This one. Okay, I hope this is clear. So what have we done is up till now we have related this. We have related 1b and 4 to each other. We have related these two. Okay, so now we can do is what we can do is we can write A1 in terms of what 4. Okay, and then what we can do is we can write A in terms of J0 and then adding the effect of 4 into it and then going on to J2 and then on to J3. This is how we are going to do. Anyways, this simple conversion is easy and we just have to what? Use this equation. This equation is the main equation that is being used everywhere. So this equation is what we have to use everywhere. You just have to put the values, right? So it is easy. That sir has also done many times in the during the live lecture. Uh, but for this, I took this equation so that you understand this. However, for assignment problems, the problems are very simple. There's not much of very complex problems. So I hope that you'll be able to solve it from this. And while solving it, just keep in mind whatever has been taught to you about the basics and everything. So yes, this is it about today's live session. And this was the 11th live session. We are going to hold the last live session next week on Tuesday, and on Wednesday there is going to be an extra session. I request that if anyone has any kind of a doubt, if anyone has any kind of a problem, then please come and join in that session. Most probably it will be at 10:30 in the morning on Wednesday, next Wednesday, 10:30 or 11, that you'll get to know mostly by this week or next week in the Monday or Tuesday, you'll get to know. But I request that you people, if you're watching the video also, that please join. If you have any doubts, then keep it with yourself. Discuss with me on that day. And that day, I'll be trying to just give you an overview about what have we have done in this whole course. How are we going to deal with those problems that we face in the practical life while dealing with such kind of a system for mechanical vibrations? And I hope that you don't have any doubt. If you have any doubt, then you can ask, or I'll end the live session for now. Okay, so I think that there is no doubt. So we'll be meeting next week again on Tuesday, 6 p.m. and then we'll be meeting for the last time on Wednesday, 10:30 or 11 a.m. And yeah, that's it for today's live session. Thank you for joining, and we'll meet next week. I'm ending the session as of now. Thank you so much.